Hello, ladies and gentlemen. My name is Mrs. Ramthen, and we're going to be learning a little bit today about protons, neutrons, atomic number, mass number, and isotopes. So here you should be able to make connections with your learning objectives that are found in your note sheet, and you'll be using this video to complete the notes as well as answer the questions in the Edpuzzle video. So up to this point, you've been doing some research on the history of our understanding of the atomic structure. So models of the atom were developed and revised based on evidence collected from different experiments throughout history. So if we take a look in particular at the Rutherford model, his research showed that there's a small, dense nucleus surrounded by a lot of empty space. And within that nucleus, we have our protons and our neutrons. So our protons have a positive charge and neutrons have no charge. They are neutral, but they are both located within the nucleus of the atom. This is the main location of the mass of an atom. So let's say we were looking at helium, which has 2 protons and 2 neutrons. If I wanted to represent that nucleus, I could use charges and some color coding to help distinguish between the protons and the neutrons. But those particles would be within the center of the atom. Now, what makes elements different from each other is going to be based on the atomic number. When we look at a particular type of element, the atomic number is equal to the number of protons in the nucleus. So you'll notice on the periodic table that they are arranged by atomic number, and each element box specifically identifies that number for the element. If there are different numbers of protons, that would mean it's a different type of element. So the data table you see at the bottom is simply listing out some of the different elements at the beginning of the table and their atomic number, which is equal to the number of protons. So any atom with only 1 proton is an atom of hydrogen. Any atom with 2 protons is an atom of helium, and so on and so forth. The number of protons defines what element we're looking at. Now, the next thing that we can record about atoms based on protons and neutrons is the mass number. What we've recorded through evidence is that protons and neutrons essentially make up the mass of an atom, and they each have a relative mass of 1. So to determine the total mass of the nucleus, we simply add the number of protons and neutrons together. Now let's say that we know the atomic number and we know mass number. Because of that understanding of how mass, protons, and neutrons are related, we can determine neutrons from that provided data. So what you'll notice is the equation listed there is just a rearrangement of the one we used in the last slide. So let's say we are looking at the element sodium. Its atomic number is 11, which we know is also equal to the number of protons. The mass number of this atom happens to be 23. So using our equation above, my mass of 23 minus 11 protons gives me 12 total neutrons, making up that difference in mass within the nucleus. In your notes, there is a sample based on carbon, You should complete the unknown values using these relationships as a sample problem. One of the ways that we identify elements is by their specific mass. So certain elements have special properties or properties of interest depending on what mass they have. So a common way to report a particular element is using the name dash its mass number. So the name of the atom of element of sodium from the last example is sodium 23. So when you read it, you don't say the dash, but when we write it, we include it. So for any element, we take its name, dash, and then insert the number of its mass. Now, writing out those names can get long, and in chemistry, we really like to use shorthand. So there is a way to write this data in kind of a short, concise way called symbolic notation. And the reason it's called that is it's based on the element symbol. So the way I like to remember it is the bigger number goes on top. It's higher up because there's more of it. And the bigger number is the mass number. Remember, that's protons plus the neutrons. The atomic number written to the lower left is the number of protons. So this is an easy way to do analysis of several different elements and compare and have that mass number and atomic number easily accessible to analyze. Now you might be thinking, okay, so we've been talking about mass and you've mentioned that there could be different masses, and we call those elements isotopes. So isotopes are atoms that are the same type of element, but different numbers of neutrons. So inherently, if I'm talking about isotopes, it's multiple versions of the same element. Because the neutrons are different, the mass numbers have to be different, because mass number is protons plus neutrons. Key part here, though, when we're referring to isotopes, they are the same elements and therefore the same number of protons. Let's look at some data that helps us compare. So carbon-12 is a version of carbon where its atomic number is 6, giving us 6 protons, and its mass number is 12. So protons subtracted from the mass number gives us 6 neutrons. This is probably the most common version of carbon. You may have also heard of carbon-14, though. This is a radioactive isotope, a version of carbon that happens to have 2 extra neutrons. So instead of having 6, it has 8, which gives us that slightly larger mass. So that version of carbon is still carbon. It's an isotope of carbon, but it is not necessarily the most common one, but it still has 6 protons. Notice that's the same between the same isotopes. So for practice, I'm going to write the symbolic notation of each of those next to their data sets. So remember, the mass number goes on the top left, our superscript, and the atomic number goes on the bottom left as a subscript. So when identifying these as isotopes, it's really easy to see in symbolic notation. The element symbols are the same, and the atomic numbers are the same, but the mass numbers are different. Our second data set involves hydrogen. Notice the atomic numbers are all 1, but the mass numbers are different. because there are different numbers of neutrons. So we would identify those as all isotopes of hydrogen, but the first set of 2 carbons are not isotopes with the hydrogen. To be isotopes, they must be the same elements.